So this is 9.3, which is essentially the beta lesson. And we're going to start with this question from the end. Which of the following gives the Taylor polynomial of order 5 approximation for the sine of 1 5/10? Okay, so you want to approximate the sine of 1.5 radians by building a Taylor polynomial of order 5. So the sine's an odd function. You want to take it that far and approximate the sine of 1 5/10. Okay, so we're going to start with that. You know enough about this to solve this question, and it's a calculator question. We're going to pause this and give you 2 minutes. Okay, so that's 2 minutes. It's order 5. So you go out to exponent of 5. It's an odd function. You know what this is going to look like? Those even terms are going to be zeros because you'd have cosine as the derivative, and the cosine of 0 is 0. So here's the sine. Here's the expansion for Maclaurin. What are we doing? We're putting 1 5/10 in there, and you get this truncated to 3 places would give you D. Okay, that's all there is to it. So, to the PowerPoint. What are we saying here? Here is the expansion about A. So this is a Taylor series. And it takes it to the nth term, yes? So it's stopping somewhere. It's stopping at the nth term, plus you have the remainder after the nth term. So here's what the remainder looks like. And this, just like on the PowerPoint, it just pops out here. And that's what the video, that's what Sal Khan was explaining to you, where this term comes from. That's the remainder. That's what this is. And he was using, and he, you know, he corrected himself. He was using E of X for error. And then he was confusing that with expected value from statistics. And then instead of taping it, he just said, it really should be an R, which it should be. So what's the deal with C? Well, that's going to help us get the maximum value, which is part of where this is, which is where it's going. Now, what happened? This whole numerator got replaced with EM, which is short for the maximum value. And then this is the absolute value of the remainder. We don't care if it's positive or negative. We care how much it's off by, the magnitude that it would be off from the function. So we have this example. Don't worry about where it says prove. Right, just keep in mind what's going on here. So there's the inequality. So we got to find the maximum value. So here, we're telling you it's the sine of X. So the sine, the highest value it takes on is 1. The derivative of the sine is cosine. The highest value it takes on is 1. So this m in the numerator is going to be a 1. That's what we're looking for. The highest value that the next term could take on when we stop here. So it doesn't matter because this thing's just going back and forth between 1 and -1 for this example. So you just move this up to the numerator. Yes. And you have this. Well, it's really 1 times that in the numerator. You want the limit of that, as x is really, really large. I'm sorry, as n gets really, really large. So what's happening? Well, the denominator is going through the ceiling. So you're going to have small over large, so it converges. But this is really this is the example that we're going to model to do the problem. So they're giving you this specific example. This is a second order approximation of the natural log of 1 plus x. And you want the interval of convergence is -1/10 to 1/10. So there's the derivative of the function, second derivative, third derivative, which you didn't need the third derivative because they wanted just to come out those 2 terms. So this is saying R sub 2, the remainder after the second order. So now what are we looking for? Well, here's where the third derivative comes in because that's the next term here that involves the remainder. So you have 2 over x plus 1, the quantity cubed. And the interval we already established was -1/10 to 1/10. On this interval, this function is going down. Right? Why is it going down? Because you have 1 plus a -1/10. So you would have 9/10 cubed divided by 2. And what? Then the numbers in here are getting larger. So as these numbers get larger, the denominator is getting larger, so the fraction's going down. So the maximum value, which in the case they showed you before for the sine and cosine was just 1, in this case it would be a -1/10. See, in the sine and cosine, they didn't go into the order because it didn't matter, because the thing was only going back and forth between an absolute value of 1, -1 and 1. Here, we're going to the remainder term, which will be the term past where you stopped, using the third derivative and setting the maximum value there. So I go here and I put the -1/10, which is the maximum value of the interval, in for x. And you get this value right here, which essentially, that's truncated, 2 over 9/10 cubed is m. So the best way to do that on your calculator, it's a calculator question, you store that. So that's the maximum area. The next term, because you stopped at the second order term, would be the -1/10 in here, the absolute value of that, so you don't need the negative, cubed over 3 factorial. Which means this, that is as much as the error can be. So, okay, we go over here and we say, what are the endpoints? Well, 1/10 gives you this, the actual value of the function. In the expansion, it gives you this. So you're off by that much. The function, take away the Taylor polynomial. The Maclaurin gives you this. You go to -1/10. The function gives you that. Maclaurin's giving you this. That's your error. Well, they're both within this bound. So you're not calculating the actual error. You're just doing that to follow through. The error has to be less than this amount that you got from what's in gold up here. All right. So the next thing's interesting, but it's not an AP topic. We'll go through this kind of quick, and then come back and leave this up here as your model to do the problem they send you to in the book. But this is clever, if you want to see this. Euler. Here's e to the x. You know how you're getting that? E to the x is its own derivative. So all these coefficients are 1. And suppose you did this. X times the square root of -1. This is not something you have to do on the AP test. This is just kind of interesting. And it gives you this. You'll do this in Calc 3. Here's the cosine. Here's the sine. And if you substitute pi for x, you get this, which has what in it? It has the two irrational numbers that you recognize the most from high school math, which would be e and pi. And it gives you the identity element of multiplication, the identity element of addition, and the square root of -1 in one identity. Okay? Very clever, but we don't need this for the test. So, back here. This is your model right up here, example 5. And we're going to pause the video and ask you to go to problem 23. All right, so let's pick up from there. This was given. Ready? You want e to the x from -1/10 to 1/10. Second order term, there's the remainder. The third derivative is e to the x. On this interval, e to the 1/10 is larger than e to the -1/10, so I use e to the 1/10 as the m value. 1/10 cubed, here's the term, the next term, over 3 factorial. So that is this number down here in scientific notation. Okay, so this number is your error bound. Then what? Well, I say, well, what's y1, which is the function, take away y2? That at 1/10, what is it at -1/10? These values. And what are you noticing? The error bound, this number, is greater than the error at 1/10, and it's greater than the absolute value of the error at -1/10. The point is, you wouldn't do this. You wouldn't check it, because if you checked it, you know the exact error. But the error bound is telling you it's got to be larger than the error in that interval. Okay. And the only reason that works is because this thing is strictly decreasing. Like if the maximum value occurred on an interior point, you'd have to use that. So this graph is strictly increasing from here to there. So the max occurs at an endpoint of E to the 1/10. Okay. So that's that for the error bound. And you notice that the second half of 9.3 is much more challenging than the geometric error. Okay.